Hello everyone and welcome back to physics class. Today we are going to be looking at position time graphs. Now before we get into the actual graphing, I want to review a few fundamental concepts that we need to know in order to understand position time graphs. And those concepts are position and displacement. Position is the location of an object or person at any given time. And we often require a reference point when we talk about position. For instance, let's say we have a hill. And on top of the hill, we have a tree. And we want to know at what position is this tree at? Well, if we were to consider that the base of the hill right here would be our reference point, we know that we would have two directions. We would have the x direction, right? How far it is to the right, and the y direction, how high up it is. So our position depends on two axes, essentially. We have our x, which is, let's just call this, let's say it's 5 meters, and then let's say that the height of this hill is 2 meters. So we would say that the location of this tree is at 5 and 2, if this were on a Cartesian plane. Now, displacement is the change in position, and we denote displacement with delta x. Delta meaning change, and x being our variable that we use to describe position. Now, there's a formula associated with displacement. And that formula is considering two positions, the final position minus the initial position. Now, if we were to take an example, let's say that we have a boulder sitting on top of a cliff, and we know that the depth of the ocean floor at this particular point is 7 meters, and we know that the height of the cliff is about 10 meters. We're considering the sea level to be our reference point. Now, if this boulder were to fall down the cliff and land at the bottom of the ocean, we would need to be able to find our displacement from this. So our displacement, in this case, we would take a look at our final position. Our final position is at -7, because if you have here, this part is 0. Above, it would be 10, and then down here it's -7, because you're below the positive axis. So it's -7, subtract 10, so we get a displacement of -17 meters in total. Now when we take a look at position time graphs, we are considering displacement as well as position when looking at these graphs. Let's take an example. So let's say we have a cat that starts off at our reference point at time is equal to 0. And this cat decides to walk over to the window, which let's say that the window is 3 meters away. And the cat's just going to sit there, kind of look outside. You're going to see a squirrel and just kind of like shift a bit, try to attack it, but he can't go any further because the window's there. And then he's going to get bored and he's going to go back to his spot that he was in originally. Now, this happens over time. So let's say it took the cat 3 seconds to get to the window. And then let's say that the cat waited at the window for another 3 seconds, which would give us a total of 6 seconds. And then let's say that the cat went back to his spot faster, so he took only 8 seconds to go back to his original spot. So when we're reading a graph like this, you're often going to be seeing these 3 different kind of scenarios. The first one being an increasing portion on the graph. Now this increasing portion indicates that there is a positive displacement. Positive displacement could be something like going forwards. It could be going to the right, or it could be going up. Those are all positive directions. Now, if we were to take a look at this flat section up here, this is the part where the cat is watching out the window. And in this particular spot, there is no change in position. He's just kind of sitting there. So that means that there is 0 displacement right here. And then finally, we have this section right here, which is the downwards slope. And this means that we have a negative displacement. This means that the cat might have moved backwards. The cat could have moved to the left, or the cat could have moved down. These are all negative directions when we're considering movement. Now, let's take a look at an example where I'm going to ask you to analyze a graph, but analyze it in a way that gives me the actual displacement for each time interval. Here is an example of a position time graph. This could represent anything, really. Like, let's say this is a small child who ran forward to go touch a tree because he was dared to go touch a tree, and then ran back and ran way past his friend that he got told to touch a tree by. And because he was so winded, he decided to collapse on the ground and just stay there. So let's analyze this piece by piece. Let's take a look at our time intervals on the x-axis and figure out the displacement that happens between each time interval. So we're going to look at this section first, right here. Now, the time interval is from time is equal to 0 to time is equal to 2. So that's our time interval. And don't forget our seconds. Now, our displacement is our final position right here, minus our initial position, which is right here. So 10 minus 0, if we're reading on the y-axis, is equal to 10 meters. And it makes sense that it's positive because we know it's going up. So this is our displacement in the first 2 seconds. Let's take a look at this part right here. This part starts at time is equal to 2, and it goes until like 3.5. So time is equal to 3.5 is when it stops. Now our final position in this case is -5. And then we subtract the original position, which is now up here, which is 10. So our displacement is -15 meters in total. And that makes sense. It's going down. We expect it to be negative. Finally, let's take a look at this part right. This is from time is equal to 3.5 seconds until time is equal to 7 or more seconds. So delta x in this case, because it's a flat line, is 0. There's no displacement happening. So this is how you would analyze a position time graph in terms of time intervals and displacement. Thank you for listening, and I'll see you next time when we start talking about velocity.